In this video, we're going to go over the steps for calculating pH for weak acids. Eventually, we'll get into the steps for how to calculate pH for weak bases, but for this lesson, we're only focusing on weak acids. Now, calculating the pH of weak acids can be challenging. This question will only give us the identity and concentration of the acid. And since it is weak, we cannot use stoichiometry. So what that means is for weak acids, we absolutely need to use ice tables to help us calculate the pH of them. So the 4 steps that we're going to go through are these. So we're going to use a Bronsted-Lowry equation to write our balanced chemical equation, then use an ice table to organize our information. We're going to write an equilibrium law expression, and for this we're going to use the Ka value in the data booklet for the weak acid that's being talked about in the question. And then last but not least, we will calculate pH by using this formula. So pH is equal to the negative log of the concentration of hydronium, and this little plus sign should be superscript just because it is representing the charge. Now, the thing about weak acids and weak bases is they have such little ionization in water that the change from their initial and final concentrations can often be negligible. Okay, so what that means is that the change between their initial and final concentrations, like there's not going to be much of a difference. Okay, so how do you know if you should ignore it? By it means ignore the X that will show up in your ice table. So you're always going to ignore X for weak acids and bases when you're trying to determine pH of them. So the reason why I'm specifying that we're going to be ignoring X, so by it means X, only for weak acids and weak bases when we're trying to determine the pH, because in our previous questions, so when we were calculating the equilibrium constants of weak acids or weak bases, we had to include the X. Okay, so the main difference here is that when you're calculating the equilibrium constant for weak acids or weak bases, you have to include the X. But when you're determining the pH for weak acids or weak bases, then you can ignore the X. So let's just go back to page 56 here and write in that little note because it is important and some students get this a little bit confused. Okay, so again, when a question asks you to find the Ka for a weak acid or the Kb for a weak base, do not ignore the minus x or the x in the equilibrium row. So what I mean by that is I mean this part right here. When you're asked to find Ka or Kb, do not ignore this. Okay, so in other words, include it in your equilibrium law expression. So include it here. And again, that's when you are trying to find Ka or Kb for a weak acid or a weak base, include this minus x in the equilibrium law expression when you're substituting in your equilibrium values. Now, going back to the questions that we are talking about, since we are finding pH for weak acids, we are going to ignore the minus x. Okay, so this does go on to talk a little bit more about ignoring x and what that will cause your equilibrium law expression to look like. So it'll be Ka is equal to x squared divided by the initial concentration of whatever weak acid that you're talking about. But let's just see this in practice here. Okay, so we're going to calculate the pH of a 0.815 mole per liter solution of nitrous acid. Okay, so this key here has a little typo, so we're just going to ignore it here. And what we're going to do is we're going to follow the steps. So step 1, we're going to write our Bronsted-Lowry equation here. So basically we're taking our weak acid and we're reacting it with water. Okay, that's the main idea of step 1. Take your weak acid, react it with water, and predict your products. So for nitrous acid, remember for your naming rules for acid, the OUS ending, you can remember it as Sprite is delicious. So that sentence means like the delicious, the us turns back into ite. So this would be like the polyatomic ion would be nitrite. So if we look at our data booklet, and we look at nitrate, that's NO2 with a 1 minus charge. And then we just put in enough hydrogens to balance out the charge there. So NO2, acids are always aqueous. Let's react it with water. Okay, since it's a weak acid reacting, we use the equilibrium arrows. And then for our products, so since this is the acid, A for away, the hydrogen is going to go away from the acid. And then towards the base. So water here is acting like a base because it's accepting a proton, whereas nitrous acid is acting like an acid because it is donating its proton. So if I imagine nitrous acid just with one less hydrogen, that's going to be NO2 with a 1 minus charge. You can check the charge either using your polyatomic ion table, or you can go, well, nitrous acid that started out with a neutral charge, I lost a proton, so 0 minus 1 is equal to -1. So that's how I'm getting the charge there. Okay, and then for our other product, we just need to imagine water just with one extra proton to it, so that's going to be hydronium. And all acids are going to produce hydronium to some extent. Okay, let's fit in our ice table here. So I'm just putting a thicker line underneath the equilibrium arrow so I can determine the difference, or just see the difference between reactants and products quite easily. All right, now we're told that we have a concentration of 0.815 for nitrous acid, and that's mole per liter. Since water is the only liquid in this equilibrium, we do not include it in our equilibrium law expression. And we can assume, since the concentration of nitrous acid was the only thing talked about, both of our products start off with 0 moles per liter, because right now we're just looking at the point of where we just have nitrous acid, but it hasn't yet reacted with water. Okay, so looking at the initial row here, if you wanted to visualize how the equilibrium or how this system is going to shift, since we only have reactants, so this big object is just representing this concentration of nitrous acid, and we have no products. In order to get this seesaw to be quote-unquote balanced here, but again, remember, the word equilibrium doesn't necessarily mean that you have an equal amount of reactants and products, right? But in order to get this seesaw to be balanced, the ball would have to move forward. So what that means is this system needs to shift to favor the forward reaction in order to achieve equilibrium. So what that means is we need to use up our reactants to produce products. So I'm saying negative X for the nitrous acid because there's a 1 coefficient in the balanced chemical equation, and same with this nitrite and hydronium ion. There's only 1 coefficient here, so that's why I say plus X for both of those. Okay. And now I'm going to be using the I plus C is equal to E here. So I'm going 0.815 minus X. So that's going to give me 0.815 minus X. However, since we are figuring out the pH of a weak acid, we are going to ignore this minus X, because this number is going to be so small, it's really not going to change this 0.815 number. However, just because we're ignoring this minus X does not mean that you can completely omit doing the ice table. You are still required to draw out the ice table. For the products, 0 plus X is just going to give you X. We are still going to include these X's. You do not ignore these X's. You only ignore this X. So ignore only this X. And why are we ignoring it? We're ignoring it because we are working with a weak acid. And we're finding pH. Alright, so I'll have to continue this question on the next page here. So after the ice table, what we're going to do, if I go back to the steps, so we just finished step 2. Now step 3, we need to create our equilibrium law expression, and we need to find the Ka in the data booklet. So this is on page 8 and 9 of the data booklet is where you'll find all the Ka values. Okay. So find Ka for our weak acid, so nitrous acid. So if I go to page 8 and 9, let's find nitrous acid. So it's right here. So remember that these values on the far right hand side, they are only Ka values. Okay, so they only apply to the substances in the acid column. Okay, so the Ka value for nitrous acid is 5.6 times 10 to the negative 4. Now, since this is a constant, just keep in mind for the final answer that we get, we are not going to use this to determine sig digs because it is a constant. Okay, so now that we have our Ka value, now we can move on to writing our equilibrium law expression. So Ka, and I'm just putting this as a reminder for myself, products goes on top, reactants go on the bottom. So for my products, for my equilibrium law expression, I'm going to write the concentration of NO2, 1 minus, times by concentration of hydronium ions, divided by nitrous acid. Oop, that should be NO2. Okay, so what I'm going to do is I'm going to plug in my Ka value for nitrous acid, so that 5.6 times 10 to the negative 4 is equal to, so my value for the nitrite ion and hydronium ion, they were both X, and then the value for nitrous acid, ignoring the minus X, is going to be 0.815. Okay, so what I'm going to do here is I'm going to multiply together the x's in the numerator, so I get x squared divided by 0.815, and then I'm going to isolate for x. So I'm going to do that by multiplying by that 0.815. And what I do to one side, I have to do to the other. Okay, so putting this in my calculator, I'll go 0.815 times by, I like to put any scientific notation number in brackets here, 5.6 second function log to get the times by 10 to the power of, negative 4, click the right arrow just once and then close the bracket, hit enter, so we get 4.564 times 10 to the power of negative 4. So that's equal to x squared. Now the opposite of squaring is going to be square rooting. And what I do to one side, I have to do to the other. So the square root of our answer is equal to 0.02136, goes on forever. Okay, so this value represents X, which, if we look back at our ICE table, X also represents the hydronium ion concentration. So we can say that this represents the concentration of hydronium. So then I'm going to write the units of moles per liter here. But we're not done just yet. Now, so we just finished step 3. So now we need to do step 4. So we're using this equation, which you need to memorize. pH is equal to negative log of the concentration of hydronium. So start out with our formula, then we'll plug in our number. So I write this ... to mean I'm using the entire unrounded number. Do not round your number until you've got your final answer. So I'm going to go negative log second function answer, close the bracket, hit enter. So our pH is 1.6703, goes on forever. Okay, so now we need to worry about sigdig. So I'm going to look at my question. So it looks like this has 3 sigdig. So my final answer needs to be in 3 significant digits. So remember that pH, the significant digits, because pH has a P in it, the sigdigs are after the point. Okay, so I'm going to start counting from here. So 1, 2, 3, there's my cutoff line. So this is in 3 significant digits. So the pH is 1.670. And remember, pH does not have any units. All right. So the next example, we need to calculate the pH of a 0.5 mole per liter butanoic acid solution here. So again, we're going to start off with our balanced chemical equation where we're reacting butanoic acid with water. Now, if you're wondering how you're supposed to know the formula for butanoic acid, you can just look it up. So let's get rid of this, clean it up a little bit, and look for butanoic acid. So I'm finding it right here on page 9. So this is the formula for butanoic acid. You are going to find it in the acid column. Okay, so remember, acids are always aqueous. React it with water. Since it's a weak acid, we write the equilibrium arrow. Now, the acidic hydrogen, it's not going to be the one in the middle, okay? The acidic hydrogen is either going to be the hydrogen at the very beginning of the compound. So when we had nitrous acid, this was the acidic hydrogen. However, when you have a compound such as butanoic acid, the acidic hydrogen is going to be part of that COOH. Okay, so this is the actual hydrogen that is going to be transferred. So for predicting our products, we're going to have C3H7COO1- aqueous plus hydronium. And that's going to be aqueous as well. So now that we have our balanced chemical equation, now we need to do our ice table. So I'm putting a thicker line right underneath the equilibrium arrow to help me distinguish reactants from products, and I'm putting the other lines roughly just under the plus signs there. Okay, so we're calculating pH, and we've got 0.5 mole per liter of butanoic acid. So I'm going to put that 0.5 in the initial row. Water is our only liquid. It's not included in the equilibrium law expression. And because our products are not mentioned, we assume that they are 0 moles per liter. Okay, so in the change row, because we only have reactants, this reaction is going to want to shift to favor the forward reaction in order to produce some products. So then I'm going to go minus x plus x plus x. So then, for the equilibrium row, this is going to be 0.5 minus x, but this is the x that you ignore, because this value is going to be so incredibly small that it's really not going to change the equilibrium concentration of butanoic acid. Okay, and again for the equilibrium row, I'm just following that I plus C is equal to E to figure out what the values are. Okay, so let's start off with our equilibrium law expression. So we're starting off with our products. So C3H7 COO1 minus multiplied by hydronium ion concentration divided by butanoic acid. So what we're going to need to find is the Ka for butanoic acid. So for butanoic acid, the Ka for that was 1.5 times 10 to the power of negative 5. So we're going to plug that in. Okay, and then for both of our products, they were both x's, and since we are multiplying them together, I'm just going to go ahead and write x squared here. And then for butanoic acid, we're going to go 0.5 and just leave it at that, because remember, we're ignoring this minus x because we're working with a weak acid and we are finding pH. We're not asked to find Ka. If we were working with a weak acid and we were asked to find the Ka, then we would have to include the minus x. But that's not what we're being asked to do. We're asked to find pH. So I'm going to multiply both sides by 0.5. So I'm going to go 0.5 times by bracket 1.5 second function log to the power of negative 5. Hit the right arrow to get out of the exponent. Hit enter. So 7.5 times 10 to the negative 6. Is equal to x squared. The opposite of squaring is square rooting. So then second function x squared to get the square root, second function answer. So we get 0.002738, goes on forever. So remember that X represents the concentration of this as well as the hydronium ion. And we care the most about the hydronium ion. So this is moles per liter. So then we're going to use this value to calculate pH. So we'll move it up here. So start off with our formula and then plug in our number. Okay, so I'm using the raw unrounded number still, so negative log. So again, remember the most common mistake is to forget to include the negative in this equation. Second function, answer, close the bracket, hit enter. So the pH is 2.5624, goes on forever. All right, now looking at our question here, looks like this has 3 sig digs to it, so my final answer needs to be in 3 sig digs as well. Now remember, pH has a P in it. You only look after the point for your sig digs. So I'm going to start counting here. 1, 2, 3. There's my cutoff line. So my final answer is going to be 2.562. And again, remember, pH does not have any units.